So now that we have a fully formed Earth and we have a moon, let's talk about what life was like in the very earliest of Earth's history and how it stabilized from a completely molten ball that was orbiting the sun to something a little bit more habitable. So, as the Earth began to cool, it differentiated into layers. And by that I mean that it went from being completely homogeneous and molten to the denser materials on Earth sinking towards the center. So that's why we have iron and nickel in the core of the Earth, right, as the densest materials on Earth. And then we have layers within the mantle of iron and magnesium with some silica. And then the crust of the Earth is primarily silicate minerals. When this happened, we had the development of the magnetic field of the Earth. Again, iron and nickel, but we know it is liquid and it formed the Earth's earliest magnetic field. This turned out to be really useful to the development of the Earth because it deflected winds from the sun, solar winds, and it helped to protect our atmosphere. So because the moon didn't have this magnetic field, it did not have this sort of protective shield around it where solar winds could basically blow off the atmosphere of the early moon. So Earth was able to retain its atmosphere, which, as we know, is essential for life and the hydrologic cycle. So as Earth begins to cool, the very earliest, very thinnest crust begins to form. And the evidence for the earliest crust is based on the oldest mineral that we have known on Earth, and that's estimated to be about 4.4 billion years ago. The type of rock that was common in some of the earliest crust are known as komatiites, which is a fun word. Say komatiite. Do it. This is what komatiites looked like. You can see they're very dark in color. They have very long, sort of elongated minerals in there. Komatiites are what are known as ultramafic rocks. So mafic is a term that you likely remember from 101, hopefully, right? Mafic means rich in magnesium and iron, right? There's the Ma for magnesium and Fic for iron. They also contain smaller amounts of silicon and oxygen. So ultramafic means ultra rich in magnesium and iron, and that's what we see in komatiites as well. Now, komatiites are very rare rocks today. Typically, komatiites have been dated to 4.4 billion to 2.5 billion years ago, so they're really not anything that we find forming in the modern. So if you go on in geology, you'll get comfortable with these sorts of diagrams. These are called ternary diagrams, and you'll see that there's three different chemicals that we're evaluating here. So if there was a rock that plotted really close to the top here of this diagram, it would be 100% rich in iron and titanium. Where if a rock plotted way down here, it would be 100% aluminum. And if a rock plots all the way over here, which is where you can see komatiites are found, you can see that they're incredibly rich in magnesium. So while it is an ultramafic rock, komatiites are primarily magnesium with very small amounts of iron or aluminum in them. So I'm going to be showing you some of these diagrams because it's important if you go on in geology that you're sort of familiar with this idea in the future. Komatiites formed at extremely high temperatures, which we would expect on a planet that's completely molten. So the minerals in komatiites did not become stable in the solid form until about 1600 degrees Celsius. So for those of you who remember a little bit about volcanoes in physical geology, most of the basaltic lava flows that we have today go up to about 1200 degrees Celsius. So this is hundreds of degrees hotter, which is what we would expect to see in the earliest Earth. So then what happened is you have these thin little plates, much thinner than our modern ocean day plates. And eventually you have these thin little plates of komatiites that begin to interact with one another. They begin to bounce into one another and they begin to subduct. So the cooler ones are going to be a little bit denser, so they would subduct first. And these plates are so small and so thin that we're going to refer to them as microplates. So what happens during subduction, as you remember, is that one plate will subduct beneath the other, and the temperature will begin to go up as that plate subducts into the warm mantle. What will happen is that some minerals will melt first and other minerals will melt at higher temperatures. So you can kind of think about this as like a chocolate chip cookie, where you put a chocolate chip cookie, maybe you warm it up in the microwave, and your chocolate chips are going to melt well before your cookie, right? So there are some minerals, just like the chocolate chips, that are going to melt at a lower temperature. So what minerals are those? So this is a diagram you've maybe never seen before. This is called Bowen's reaction series. So there was a scientist named Nicholas Bowen who did a lot of experiments with lava flows, and he determined that certain minerals cool at really high temperatures and other minerals form at fairly low temperatures, just like we were talking about with the chocolate chip cookie in the cookies. So minerals that start to melt at pretty low temperatures, like 800 degrees Celsius, are your felsic minerals. They're your lighter minerals like quartz and muscovite and orthoclase. And you remember these from one of your early activities in this class where we reviewed some of your minerals from Geo 101. So these are your lighter colored minerals. Your darker, sort of grayish minerals that you find at subduction zones today are here in your intermediate minerals. And then your really dark minerals that are really rich in iron and magnesium, right? They will form at higher temperatures. So when we have subduction, again, it starts to get warmer. And as it starts to get warmer, those cooler minerals are going to melt first. So if those cooler minerals, these lighter colored minerals, come up here and they start to sort of intrude into this komatiite-rich crust, we're taking something that is ultramafic and we're adding in some felsic stuff. So we're taking something that's really, really dark colored and we're starting to add in some lighter colored minerals. So what that does is it's going to change the composition of what is forming here. And it's going to change the composition of the magma from ultramafic first, where you have your komatiites that are melted, to mafic, to andesitic. And so that is how we start to have the first andesitic volcanoes form on Earth, and eventually the first chains of islands, like we see here, in island arcs. And I know you remember how island arcs form, but we're going to review it very quick. But here we have the subduction of two microplates during the Hadean, and we start to have those cooler temperature minerals, those felsic minerals. They're going to rise up through the crust. They're going to melt through that crust, and they're going to change the composition of it. So it will no longer be ultramafic. First it will become mafic, and then it will become andesitic, and we will start to see that composition change in some of the island chains that will form as a result of the subduction and melting. So here we have the eruption of a volcano that eventually will rise above sea level, and you have the emergence of an island. And you will have this not in just one location, but you'll have it all along a subduction zone. So you'll have a chain of islands begin to emerge with andesitic composition. These are stratovolcanoes or composite volcanoes, if you remember that from physical geology. And this is how we had the first island chains form on these very thin layers of Earth's earliest crust. So this becomes then stage 2 of crustal formation. So stage 1 is the beginning of oceanic crust, and this is how we begin to generate continental crust, because the next thing that happens is that these island chains begin to collide with each other. So here we have two different chains of volcanic islands, and there are subduction zones between, and they get closer and closer. And we know that this crust is going to be so low density that it won't be subducted. So instead, what will happen is it will collide and begin to create microcontinents. And through partial melting of some of this crust, as these plates collide and there's a ton of heat and pressure, you will eventually, if we were to go here, I'll go back to Bowen's reaction series in just a second, eventually the addition of more and more of that felsic mineral, more and more of those granitic minerals, you'll eventually have the generation of felsic magma. So let's get out of here for a second and go back to Bowen's reaction series maybe. Oh, I closed it. No. So that was on this slide. Sorry about that. Open link. All right, so we have these intermediate andesitic lavas, where we have our volcanoes. This is our island chain. And then as we add more and more quartz to it, more and more muscovite and more orthoclase, we slowly shift the composition of that crust from being andesitic in composition to eventually being felsic in composition. So this is how continents are made, really. It was through the addition in the collision of these island arcs to eventually form the first granitic crust, or the first real thick continental crust in Earth's history. And that's how continents are formed, kids. So let's now talk about how oceans are formed. And you can see the formation of the ocean is at about the same time as the formation of the Komatiite rich crust. So the composition of early oceans is primarily the result of carbon dioxide and water vapor that are the result of volcanic outgassings. So remember that early Earth was really hot. We just had the very beginnings of plate tectonics, right? We have heat from lots of radioactive decay. We still have heat of accretion, and we have really active plate tectonics, really thin crust, lots of melting. So with that in mind, you have lots of volcanic activity on Earth. Here is a diagram of a volcano, and you can see that primarily what comes out of it is hydrogen, water, carbon dioxide, nitrogen, which is largely a gas that just floats around in the atmosphere, and then water vapor that eventually condenses into liquid water. So there's also the addition of water from impacts from extraterrestrial objects. So during Earth's early history, you have many more of those impacts. And so comets especially will contribute water to the Earth's atmosphere. Eventually it cools enough on Earth that water vapor begins to condense into liquid water and then fill the lowest of the ocean basins, or fill the lowest land on Earth, and it's just like filling up a bathtub. The lowest elevations are filled first. However, what's important to know is that these early oceans are very acidic because in addition to carbon dioxide, which dissolves in water and becomes a weak acid, there's also a lot of sulfur that is coming out of volcanoes and enough of methane as well, that when this gets into the oceans, it creates a very acidic ocean. Similarly, and that's how the oceans were made. This is a big lecture today. Similar to the composition of the oceans, the atmosphere is also primarily controlled by the composition of gases that come out of volcanoes. And one of the things you'll notice is that nowhere coming out of a volcano is free oxygen. And remember, one of the terms we learned for no oxygen is anoxic. There is no free oxygen in Earth's early atmosphere. We know that because we have very little evidence. We have some old rocks, but we have very little evidence for oxidation in those old rocks. So today, when we have rocks or minerals that have oxygen in them, the oxygen in the atmosphere will react with those rocks and oxidize those minerals. So that's like why metals rust, for example. Any free oxygen will react with those metals. When we look at ancient rocks, we see very few oxidized metals. We see very little rusting. In rocks, a lot of times we'll see that present as hematite or other oxidized minerals that you folks haven't necessarily learned about yet, but there are a handful that exist. So the evidence we have that the Earth's atmosphere was anoxic is that when we look at Archean rocks, and we don't have any rocks really from the Hadean, but when we look at Archean rocks that are the remnants of that were formed initially during the Hadean Eon, those rocks are often dark in color. And that dark color typically indicates the presence of iron, but no oxygen to oxidize that iron to create that red rusty color. Other things that we see in Archean rocks are what are called detrital pyrite. So detrital are particles that are shed from mountains and roll around a little bit in streams. So if you were looking at a stream deposit, and this is a conglomerate, and we can tell that because this is a 1 centimeter bar scale, just so you know. So we can see particles that are rounded, right? And are a variety of grain sizes, which is what you'd expect to see in a conglomerate. However, these are grains of pyrite. So the chemical formula for pyrite, if you remember from 101, is FeS2. 1 atom of iron and 2 atoms of sulfur. So what happens to iron typically on Earth, you don't have to write this down. I just want you to know this because it turns out chemistry is like unbelievably important, even though it's not always my favorite thing to do, but chemistry explains everything. So under our normal conditions, with our oxygen levels in our atmosphere, what typically will happen is that 2 atoms of pyrite, so this is FeS2, this is our pyrite. Pyrite will react with oxygen, O2 is oxygen gas, and it'll react with water. So normally in a stream, pyrite will react with oxygen that's dissolved in the water and the water itself, and it'll break down. It'll break down into iron, some hydrogen ions, and some sulfate. So what happens then is that this is what makes that iron red, because that oxygen will start to react with the mineral. But we don't see that when we look at Archean rocks. We see these grains of these grains within this conglomerate that were formed during the Hadean, and they didn't react with oxygen because there was no oxygen around. And so these grains of pyrite just like rolled in stream beds, which must have been such an amazing sight if you think about it, right? Because pyrite is known as fool's gold because it's a sparkly gold mineral. And here you have like rivers full of like rolling balls of pyrite down the stream. Like that's awesome. That's really cool. Everything else on Earth would have been terrible. The atmosphere on Earth would have been totally anoxic. I'm sorry, my dog is adjusting herself. Are you all right, Rose? And the sky would have been red because there would have been a high amount of carbon dioxide and methane in the air. So the sky would have been red. It would have been anoxic. It would have been incredibly hot. And then you have rivers full of like golden pebbles. It would have been quite a time to be alive very briefly. So those are, by the end of the Hadean, which is where we are now, by the end of the Hadean, Earth is very different, but the pieces are set up that will lead us to what our modern day Earth looks like. And so you will find this at the end of each of these eons. So at the end of the Hadean eon, we have continents, we have oceans, we have an atmosphere, we have a magnetic field. And that is pretty much it. Things are going to look incredibly different at the end of the Archean, though. So we go back to our time clock here. The Archean is a big chunk of Earth's history. It is 30% of Earth's history. It starts 4 billion years ago and it ends about 2.5 billion years ago. So let's talk about the hydrologic cycle during the Archean. During the Archean eon, the atmosphere is still anoxic, and at the beginning of the Archean, the oceans are also still very rich in carbon dioxide and methane, We know that because when we look at the rock record from the Archean, there are no carbonate rocks. So carbonate rocks, I feel like we've talked about this before, but just in case we haven't, carbonate is this molecule, which you learn in 101, but sometimes people forget things. So carbonate is CO3. So there are a couple minerals that we've learned about that have this carbonate ion, right? We've had calcite, which is CaCO3, and then we've had dolomite, which you don't need to worry about, but it is CaMgCO3 too, which is fine. Don't worry about that. But regardless, there's none of this in the oceans during the Archean, and we know because one of the really identifiable characteristics of calcite is that it reacts to acid, right? So there was so much, and when it does, it bubbles and it turns into carbon dioxide gas. There was so much acid in these early oceans as a result of volcanic outgassing that any carbonate minerals would have dissolved. So we don't have the accumulation of carbonate-rich rocks. But we do have an atmosphere that is full of acidic precipitation. So we have clouds that are full of much more acidic water vapor than we have today. So when that acidic water vapor turns into acidic rain and acidic snow, what happens is it falls on those very small microcontinents and volcanic arcs. And when acidic rain falls onto volcanic rocks, it rapidly weathers them. And so what happens to those volcanic rocks, and this is how we're eventually going to get to a salty ocean, not yet, but we're going to go in that direction eventually, is that those volcanic rocks get broken down and weathered. They get carried by streams, and those streams eventually flow into the oceans. So the acidic rain weathers rocks, and those rocks, when they flush into the ocean, are full of calcium, iron, and sodium. These are pretty common in continental andesitic type rocks, and when these flush into the ocean with enough concentration, by the time we get to our next eon, we will eventually, by that point, by the time we get to the Proterozoic, about 2.5 billion years ago, the ocean will be full of those salts. So, and that will also, we'll learn about how that will then eventually start to bring down some of that acidity. Because so we know that the opposite of acidity is being basic. So basic is a higher pH. Things that are acidic have a low pH. So when we add in a lot of these elements from Oh, sorry, I just sneezed. Okay. So when we add in these salts, so you can think of sodium, right, as a salt, but iron and calcium in its ionic form is also a salt. So when we weather these rocks, we're adding salts to the oceans. Some of these salts will be used for a variety of things, and we'll talk about what when we get closer. But this is how the ocean is going to become less acidic, more basic. Today, the pH of the oceans is about 7.8, and we know that pure water is 7, so it's a little bit basic today. And this is how, from the weathering of these volcanic rocks. So let's talk about these rocks. Archean rocks are kind of crazy. So Archean rocks have no fossils in them, not any of them. They can be correlated using radiometric dating and then by also understanding some of their geology. Archean rocks are often divided into provinces. Provinces are rocks that have similar ages. They might have similar trends on folds and faults, like they might all be oriented sort of northeast to southwest or something like that. We can see those rocks are exposed in the shield. Remember, the shield are Archean or they are Precambrian mountains that have been basically weathered down into stumps. And the biggest exposure of the shield is certainly in Canada. We have a little bit of the shield that's exposed in the Adirondacks and the high peaks of the Adirondacks. I saw in discussion forums that some of you folks have spent some good times here. We also see some shield in Wisconsin and in Minnesota as well. But the vast majority of shield is exposed in North America anyway, in Canada. So I think this is a good time to talk about bias. There's tons of places where the shield of the Earth is exposed. And if you were taking this class in Australia, you would be focused much more on looking at the Australian shield, which is also super old and super cool. But the reality of it is most of us who go on to work in geology and are taking classes in the United States end up working in the United States. So this is definitely a course that is biased towards North American geology, which you can see is going to be plenty complex. So we're going to be looking at some rocks within the shield today. So these rocks are then, now that you can see where the shield is exposed, they've been grouped into these very large provinces. So this is the Superior Province here that is closest to us. And all of these orange provinces, like the Slave Province in through here, a lot of these are abbreviated, are going to be grouped based on basically a whole bunch of little microcontinents that get stuck together and have similar trends. So within each of these provinces, there are these really strange belts. They're called Granulite greenstone belts. And we're going to look at two of those provinces that we just mentioned. So here's a map of Canada again. And you can see the Superior Province and you can see the Slave Province. And these are called Granulite greenstone belts. We're going to talk in the next few slides about what granulites are, what greenstones are, and why they have this crazy striped pattern, which you should hopefully be able to relax your eyeballs a little bit and see that there are stripes of dark green and light green. And you can see those. They're a little bit more deformed in the Slave Province, but in the Superior Craton here, they are very, very straightforward. So when I use the word granulites, and you might want to pause this video at various points to take notes, and you should probably be doing that throughout like the whole course, but here is a picture of some granulites in Georgian Bay in Ontario, Canada, which is beautiful. They are called metagranitic gneisses. So if you remember, gneiss is a metamorphic rock, and there's the word meta. So whenever we're talking about something and we say that it's metagranitic gneiss, it means it's a metamorphic rock named gneiss that used to be granite. So the granite was metamorphosed into the gneiss. So the granite is the parent rock of the gneiss that we see today. And when we look at the Georgian Bay outcrop here, you can see really distinct bands like you can in gneiss. It's one of those really characteristic metamorphic rocks that has segregated minerals into light and dark stripes almost. So how did these metagranitic gneisses form? So we know they used to be granite. They are interpreted to be metamorphosed volcanic islands. And those volcanic islands were granitic and andesitic in composition. So you have these volcanic islands, they eventually get metamorphosed. So the thing to keep in your head here, because the greenstone belts are kind of complicated, is that granulites are metamorphosed islands. All right. They are also then interpreted to be protocontinents or microcontinents that are very narrow and steep-sided because they're basically just chains of volcanic islands, right? They have rugged coastlines, kind of like you would expect where you have a volcano very close to a beach. You're going to have sort of rapid weathering, but not like a long stream necessarily. If you're talking about a volcanic island, there isn't necessarily a great distance between the source rock, or the provenance is a word that you'll be learning in lab, and where that rock then gets deposited. All right, so let's talk about those greenstone belts. So the granulites are metamorphosed volcanic islands. The greenstone belts are the region in between those volcanic islands. So this dark brown stuff here, and we're going to look at this in more detail on the next slide. These are the granulites. So granulite 1, granulite 2, granulite 3. So the greenstone belts are these features in between the granulites. So they are interpreted to be metavolcanic and metasedimentary rocks. So building off what we just said, metavolcanic means they're metamorphosed and used to be volcanic, and metasedimentary are metamorphic but used to be sedimentary rocks. What's cool about these granulite and greenstone belts, and we can find them in the shields and the cratons of all continents, which means that this is a process by which all continents were being built during the Archean Eon. They are formed in these synclinal belts, and we'll talk about why that is in just a second. But it again has to do with the order of melting for minerals. So if you remember the word synclines are structures that are downward folds, kind of like what you see here. You probably remember that from physical geology, where anticlines are upward folding folds in rocks and synclines are downwarped folds in rocks like we see here. So how did these synclinal features form between two different volcanic islands? All right, well, the clue comes in when we look at the structure of the greenstone belts. So again, here we have a granulite 1, granulite 2, granulite 3. These are going to be metamorphosed later, but we can think of them as volcanic islands from now on. And we see a bunch of things. We see this yellow crystalline pattern here. These are some granitic intrusions. We can see ultramafic volcanics. So let's stop here. Volcanics mean that they erupted, that they actually hit the surface. They did not form intrusively, these formed extrusively. And we know granite intrusives cooled inside the earth. So above the ultramafic volcanics are mafic volcanics, and then felsic volcanics, and then some sediments. And we can see that these granitic intrusions have to be younger than all of these volcanic rocks and the sediments, right? Because they intrude through them. And that, remember, is the principle of cross-cutting relations, where younger volcanic features will cut across older ones. So these greenstone belts grade from ultramafic to mafic to felsic sediments. The composition of these ultramafic volcanic rocks are primarily komatiites. Remember, komatiites are ultramafic rocks that formed the earliest crust, and they have a tremendous amount of magnesium in them. Those are then overlain by other volcanic rocks. This volcanic rock is typically basalt. Basalt is mafic. It's not ultramafic anymore, right? There's still a lot of iron and magnesium, but not nearly as much. And then we get up to our felsic volcanics, which are primarily some rhyolites, which is what happens when granite erupts. You get some rhyolite, and some andesites, and these have erupted then through here. What I'm going to do, these have erupted and formed this orange belt here. What I'm going to do, I think, is to put some links. I'm going to write myself a note right now. I'm going to put some links in the folder so that you can kind of review what these rocks look like. Rocks from greenstone belts. Because I recognize that it's probably been a long time since you thought about rock identification. So I'll put some links to some pictures in there so to kind of refresh your memory. So this is an important trend here. We started off with rocks with a ton of magnesium, then slightly less magnesium, and then very little magnesium, and then some sediments. So that's not random. Another important thing, the reason we know that these are volcanic rocks and not intrusive rocks is not only because of the grain size. Remember, when rocks cool extrusively, they're going to cool much quicker, and you're going to see no visible crystals, and intrusively, you're going to see visible crystals. So in addition to having a fine-grained, or what we call an aphanitic texture, are all these words coming back? Are you cringing? It's going to be okay. In addition to having an aphanitic or a fine-grained texture to these rocks, they also have what are called pillow structures. So the pillow structures, remember we learned about pillow basalts. You can have pillow komatiites, pillow rhyolites, pillow andesites. They form, here's a 18-inch long rock hammer, and you see these ball structures. These are the pillow structures that indicate that this lava erupted into probably a shallow sea, but minimally into the surface, submarine volcanism. So the sedimentary rocks that we see at the top are of these synclinal structures are shale, conglomerates, and gray wackies. And we'll talk about how this particular structure could have formed because it's pretty cool. So we're going to talk about a 3-step emplacement of these greenstone belts. So here is your standard garden variety subduction zone with a caveat. So this is what we do in 102. We basically take everything you learn in physical geology and we just add a little bit of nuance to it, a little bit of detail. So remember that this is a convergent plate boundary. So what that means is two things. Most students know that a convergent plate boundary, especially at a subduction zone, means that this plate is moving this direction. But it also means that this plate is moving in this direction. And what happens is as we start to build up some rock here, right? We have accretionary wedges that are forming here, maybe a melange. We're adding to the continent right here. What ends up happening is that we're still pulling this part of the continent away. And what we end up doing, not we, but what continents end up doing is they undergo a lot of stretching on the other side of those volcanoes. And this is tensional stress or extension. So the crust starts to get really thin here. So here's our granulite, right? Our granulite are these volcanic islands. And there's also going to be another granulite right here. This picture just doesn't show that. And this is where our greenstone belt is going to form. And this is called the back arc basin. And that's because this is the volcanic arc, the chain of volcanoes on land, and this is behind the arc. So it's the back arc basin. All right, let's get rid of my pen for a second. When I was first learning about this, I thought it was really useful to think about this in terms of, oddly enough, corrugated cardboard. And that's because I think the structure of it makes a lot of sense to me. So these portions here that are folded up, you got to think of these as those volcanoes, and they're in line one after another. So one chain of volcanoes, and then in here is where a greenstone belt is going to form. This is going to be that granulite island, and this is where we're going to have a greenstone belt form. And you'll see what happens to, but this explains that striped pattern though, right? So we'll have a chain of islands here, and then a greenstone belt, and a chain of islands here, and a greenstone belt. So that's going to explain that pattern that we see when we look at the map of Canada. So as that basin, that back arc basin, starts to get thinner and thinner, we're going to bring back an idea from physical geology, and that is decompression melting. Decompression means we're reducing the pressure and it causes melting. That happens at mid-ocean ridges, right? Where the pressure on the mantle gets really low because the plates are moving apart, and it causes melting. And when it causes melting, it comes up from below. So we're going to have melting that's going to occur here, and this is where our volcanic rocks are going to form. And then the sediment will be coming in from the surrounding granulites that are eroding as well. So we're going to have volcanism as a result of stretching in the back arc basin, and then we're going to have erosion and sedimentation from those adjacent granulites. If you have to listen to this lecture a couple times, please do it. This is like dense stuff. This is about as complicated and as crazy as things are going to get this semester. The formation of continents and these crazy Archean structures. So the next thing that happens, remember we said that there's a bunch of these granulite island chains. They're going to collide with each other with adjacent granulite chains. So we have one granulite chain here. We have our eruption of our volcanics here. We have our next chain of granulites here. Guess what's going to be riding along on this oceanic plate? We're going to have another granulite chain smash in here. When this all starts smashing together, it's going to close up that back arc basin. So then we're not going to have any more stretching. And if we don't have any more stretching, we no longer have decompression melting. We are, however, going to fold up that basin. There'll be some faulting as we're folding it up after that as that basin is closing up, and any residual magma that's left around is going to intrude its way up. So that's how those granitic intrusions are going to form. So remember this diagram? So what we have here are those granulites, right? That's in gray here. So the reason that these rocks go from ultramafic to mafic to felsic is because as those rocks are, as that magma and then becomes lava, as it erupts through, what it'll do is first it'll hit that cold air and cool water, and it will cool into those pillow structures. I'm going to do this again. So that's how, oh, not that, but that's fun too. Okay, so we have this first layer of lava come up through. Then we have more decompression melting going on down here, right? Because this is our basin. And then that next stage of lava that has to go through has to move its way up through these ultramafic rocks, and they start to cool off a little bit. And remember, those first minerals that are going to melt, those first minerals, the chocolate chips of the chocolate chip cookies, are going to be really rich in felsic stuff. So felsic minerals are light. So when you take our really dark rocks and you start stealing the white minerals and mixing them into the lava, that lava is going to become lighter and lighter the more light minerals that you mix in. So as we move up through this section, we're adding more and more of the silica. We're going to melt any silica out of this mafic rock and carry it up. That lava is going to carry it up when it erupts here into this layer of felsic rocks. So what we see, the trend here, there, is going to be as that lava moves through thicker and thicker chunks of crust, there is going to be less iron and magnesium, which is going to be our ultramafic and mafic elements, and we're going to have more silica. And the chemical formula for silica is SiO2. And then the source for the sedimentary rocks is just the erosion from the surrounding granulite belts that are going to be deposited into that basin. So again, this is the crazy stuff. You can read over this again, listen to it again, look at the diagrams, and ask questions when you have them. So then we can look at the southern superior craton. So again, this is a chunk of craton. This is what's called a geologic map. I should have explained this a little bit earlier. A geologic map is basically if you were to scrape all the vegetation and all of the soil off of a rock, off of a location, and just look at the rocks that are underneath that location. That's what a geologic map shows you. So here's a geologic map of the southern superior craton. The greenstone belts you can see are all labeled here. The English River, the Barrens, Greenstone Belt. The granulites are dark green, like the Wawa Belt, the Wabagoon Belt. And so they are in this striped pattern because you have granulites, so island chain, and then the syncline, and then the basin between them. Island chain and the basin between them. Island chain, basin, island chain, basin, island chain. It's really cool. So this is the interpretation for that, is that, remember that Wawa here, that's that dark green, and then you have the Quetico belt in light green next to the Wabagoon belt. So look at island chain, greenstone belt, island chain, greenstone belt. So they fold up almost like an accordion, and that is how we're going to build these provinces of land in the Archean, and they will eventually bump into each other, and they will build the continent of North America and the continents of all of the globe, really. So that was a lot. Answer some questions on this lecture because it is dense. It is really, really dense. And then afterwards you are rewarded with a very fun video of the Archean life. But that is pretty much going to bring us to the end of our exam 2 material. So once you're done with this, once you understand it, once you practice it as much as you need, go ahead and take the exam 2 in lecture. All right, take a deep breath. You just got through some really heavy stuff. You got this. And if you feel like you don't reach out to a classmate, reach out to me. I am sitting in this desk waiting for your email.